Okay, 6-9, number 3. This is an angular momentum question, which this is one of the weird angular momentum things where, like, you don't actually need to be spinning in a circle to have angular momentum. You can actually just be going in a straight line, but relative to some random point, you can have angular momentum. I kind of think about it like if I had my falling stick and I had an object coming in and it hit right at the pivot point, well, relative to this pivot point, and they collide, no rotation would happen. So there's no angular momentum after the collision, which means there was none before. If I throw or I hit the stick, I throw a ball at the stick and I hit it in the center, then yeah, the stick will rotate and I'll get some angular momentum in the stick. Well, that means the thing moving straight must have also had some angular momentum to begin with. So even though it's like a moving straight at a constant velocity object, relative to this hinge point, there is some momentum and there is a lever arm. And so we do have some angular momentum based on this distance away from that pivot point. If I throw the ball at the end point and I hit it with the same force, I'm going to see more angular momentum in the stick after the collision, which means the ball or the object must have had more angular momentum before the collision. So even though this moving object is moving with a constant velocity in a straight line, it can have different amounts of angular momentum depending on where that arbitrary pivot point is chosen, like if you know you're going to run into a stick. So no angular momentum, middle amount of angular momentum, the maximum amount of angular momentum, but it's the same straight moving object in a straight line, which shows us, right, that angular momentum is the position crossed with the linear momentum. Do not confuse angular momentum and linear momentum. Angular momentum cannot come from linear momentum. Linear momentum cannot become angular momentum, or vice versa. There's no transfer of linear momentum to angular momentum ever. You have to justify there being angular momentum, and it gets conserved, and there has to be a separate amount of linear momentum that it gets conserved, where an external force will change your momentum and an external torque will change your angular momentum. So again, you can kind of think of that too. Here, applying the force at the top, there's no torque from that force, more torque, more torque. So no angular momentum, middle amount, most. So what do we got here? Relative to the origin, we're going to look at a projectile and how its angular momentum is changing as it flies through the air relative to the origin. So at the origin, immediately at launch, the position is 0, right? It hasn't actually moved anywhere. It does have linear momentum because we've launched it, but it still hasn't moved from the origin, so we don't have any angular momentum yet, right? We've just got some linear momentum, which is also going to change as it flies through the air. But we have no angular momentum at the start. Boom, 0. So then this thing flies, it gets to the top, and now it's moving horizontally. So I'm going to take the position vector here, and I'm going to cross it with the linear momentum. So cross products meaning make the two things perpendicular. So I'm looking for the position vector and the velocity vector and how perpendicular they are. In this case, I think it's easier to break the position into a vertical component called the max height, and then the linear momentum is determined by the horizontal component of the initial launch velocity. So we've got that here. So height, vertical position, horizontal velocity, cross product says use the perpendicular bits. So I'm going to use the height. I'm not going to go over how to find max height of a projectile. Hopefully you can do that. If you can't, do some review. And then the linear momentum is mv, but the v at the top is just the x component, so vi cosine theta for the angular momentum at the top. At the end, when it lands, here its position vector is something we might have called the range, or the horizontal range, which is just the horizontal distance from the origin to where it's landing. So you could use the range equation or some other kinematics. You can figure out how far that thing goes. What's the range? Because you're going to need that. And since that is horizontal, then in the next case, it's easier to find the vertical component of the velocity and the momentum so that we can cross product those together. So in that case, here it gets back to the same height. We have the same initial velocity. It would again be at the same launch angle, just below the horizontal now. So the theta is the same. The VI is the same. It's just moving in the down direction now. Boom, boom. So you have your position vector, which is the range. You can figure that out. And then using the vertical component for our cross product of mvi sine theta. And there you go. And then the last question is, what force or what torque is causing the angular momentum? And it's going to be the weight force. If you were to draw the weight force, you can see that it's definitely changing the angular momentum in the right-hand rule direction. There's also a right-hand rule torque from the angular momentum, or from the weight force. So that is why the angular momentum is changing, right? It starts out at 0, it reaches some amount at the top, and then it's a different amount when it gets back to the ground. And that's all based on two things. One, the speed as it's changing, as it flies through the air, and how far it is from the original point and how perpendicular that position is to the velocity. So the whole time you do have that vertical weight force, and you would then be crossing that also with the position vector to find the torque, and that is variable based on position, so we get a varying change in angular momentum with that variable torque.